Hello, my name is Bruna. The study on the flow of soft microcapsules through a constricted capillary is part of my PhD research developed at PUC-Rio with Professor Mariano Michelon and Professor Márcio Carvalho. Microcapsules are formed by a core material involved by a shell. They range in size from 1 micron up to a few millimeters, and they can have a single core or multiple cores. Microcapsules are applied in several sectors of industry when a physical barrier between the core material and the external environment is required. They allow the incorporation of sweeteners, colorants, vitamins, and probiotics to different foods and beverages. They have been used for encapsulation of cosmetic components as essential oils, anti-aging elements, and skin moisturizing agents. Microcapsules can also carry the rejuvenator needed in self-healing methods of asphalt pavements. In the pharmaceutical area, they enable site-specific and sustained drug delivery, increase shelf life, reduce adverse reactions and side effects, and they can also act as an alternative administration mode of some medicines. Basically, microcapsules isolate their cargo and ultimately release it in a controlled way. In general, the release is a consequence of mechanical rupture via degradation, dissolution, or melting of the shell, or diffusion through it. Different triggers can be applied to activate the core release, such as temperature, pH, osmotic pressure, and external stress. Dynamics of deformable microcapsules in confined flows is relevant for medical, pharmaceutical, food and cosmetic industries since constrictions are present in physiological systems as arteries and veins, for example, and capsules are regarded as adequate models for living cells. Moreover, constricted geometries can be used for triggering and controlling the release rate of a cargo by applying the necessary external stress to the microcapsule. Besides that, recent studies have shown that microcapsules may also be used in enhanced oil recovery as fluid mobility agents that block original water paths, resulting in increased volumes of oil recovered. In addition, these same capsules can be filled with chemicals acting as carriers for target delivery in specific areas of the pore space. The adequate properties for each kind of application are different. Capsules used as vehicles for triggered delivery, for example, must be easily ruptured at certain conditions, while capsules used to improve mobility ratio for IOR cannot rupture. So the key is to define the right technique and material to produce the capsules you need so you can control the encapsulation and release processes according to the desired application. So, the goals of our research were to design microcapsule suspensions with tunable mechanical properties so we can set the diameter and the shelf thickness depending on the application, study the flow of a single suspended microcapsule through a constricted capillary, defining the conditions at which the microcapsules rupture or not, and measuring the extra pressure drop they cause as a function of flow conditions and microcapsule properties. Let's start seeing the microcapsules production. Our microcapsules are basically oil in water and oil double emulsions that go by a gelation process, and therefore they can be used to protect and deliver a wide range of hydrophobic active compounds. In order to compose the microcapsule, sunflower oil is used as core, here in yellow, and as continuous phase in which they are suspended. While gel and gun, which is a biopolymer capable of forming hydrogels in the presence of cations and widely applied in cosmetic and food products, for example, is used to form the shell represented here in blue. Because many applications for the gel and microcapsules require an oil-free capsule dispersion, we apply a recovery process to change the continuous phase from sunflower oil to acetate buffer after producing the capsules. There are many methods to produce microcapsules. Conventional techniques as spray drying, extrusion, conservation usually require 2 emulsification steps and present poor reproducibility and poor control of size and shelf thickness. Therefore, we used this 3D microfluidic device here that is built in a microscope slide and combines cold flow and flow focusing and allows the production of oil in water and oil templates with tunable mechanical properties. The device has two aligned round capillaries inside the square capillary, the injection on the left and the collection on the right. The inner phase flows inside the injection capillary, while the middle phase flows in the space between the injection capillary and the square capillary, and the continuous phase flows in the opposite direction, and the space between the collection capillary and the square capillary. As I mentioned before, after producing the capsules, we disperse them in acetate buffers, so in the end we have a oil in water system. Then, to produce perfect monodispersed microcapsules, we have to define the process parameters, meaning phases, composition, we already defined flow rates and device dimensions that lead to this intermittent dripping region flow here. It basically depends on the balance between the pinning and drag forces acting here in the tip of the injection capillary, so that the breakup of the inner and middle phase happens at the same time and the same position. So we fixed each flow rate at a time to form operability windows like this, where we can see the flow rates required to achieve the dripping regime and form our microcapsules, which only happens here inside the red curve. And also the combinations that do not form any capsule, if the middle phase flow rate is too low or if the continuous phase flow rate is too high, or form microcapsules with multiple cores that we are not interested in now. Then we describe the diameter and the shell thickness of the microcapsules as functions of the process conditions by analyzing each point here inside the red curve. So, we established that we could control the diameter of the microcapsules by changing the flow rate of the continuous phase. The lower the flow rate was, the bigger the capsules would be. By doing so, we are able to produce microcapsules with diameters ranging from 130 to 260 micrometers. Then we found out that we could broaden this range by simply changing the device dimensions, so even smaller microcapsules could be produced. Besides that, we also saw that the shell thickness depended almost exclusively on the flow rate of the middle phase, which is the gel and gum, and we then produce capsules with very thin and very thick shells. After producing several batches of monodispersed microcapsules of different sizes and shell thicknesses, we selected some of them to use in what we call the constriction experiments. So this is the experimental setup for the constriction experiments. The same geometry was used in all tests. It is a round capillary with a diameter of 300 micrometers and a constriction of 100 micrometers. A fluorescent system was applied to feed the suspension through the capillary at constant flow rates and measure the pressure response. An inverted microscope equipped with a high-speed camera and a computer was used to monitor and record real-time images of microcapsules flow. This is a table of the batches of microcapsules used in the tests with their diameter and shell thickness. All of them are smaller than the glass capillary, but bigger than the constriction diameter. Here is the ratio. To enable pressure drop measurements, microcapsules were suspended in a saturated sucrose solution to increase the carrier fluid viscosity, and results were all obtained at a flow rate of 0.2 milliliters per hour. Microcapsules can undergo two types of deformation during the experiments, depending on their characteristics, as will be explained later. It can either be a reversible deformation, in which the microcapsules return to its original shape after flowing through the constriction, as shown here on the video on the top, or the microcapsule deformation is too severe, leading to shell rupture at a certain level of pressure drop during its passage, as shown on the video on the bottom. We use MATLAB to further analyze the images and identify if the capsule was intact or not during the entire flow. Here you see a typical outcome of the capsule's nose position x as a function of the time for the reversible deformation case. In this case, the capsule diameter was around 144 micrometers. Position equal to 0 here indicates the middle of the constriction. So before it, the microcapsule is flowing in the direction of the constriction. It is even possible to see a change on the curvature here, indicating an acceleration as the capsule draws near to it in the convergence zone. Then the capsule gets trapped and almost stops for a long time while trying to force its way through the constriction. When it finally makes it, the position varies very fast, indicating that the capsule floats to the divergence zone. Looking more carefully to the capsule's shape during the flow, we see that microcapsule arrives to the convergence zone as a sphere. This moment is related to the first pressure plateau here that indicates the pressure needed to push only the continuous phase through the constriction. Then it starts deforming to fit to the constriction, presenting a slug shape. This partially blocks the flow, causing an increase in the pressure response. The slug shape remains inside the constriction until the microcapsule reaches its maximum longitudinal elongation. Then the microcapsule is expelled from the confining geometry and its rear becomes slightly concave. We see on the images that the membrane integrity is preserved, which can also be verified by the absence of leakage. The pressure starts dropping, and after some time, the microcapsule recovers its original shape, spherical shape, and the pressure reaches back the initial plateau. The changes on capsule's shape can also be noticed by the variations of Ly and Lx with the position, which are the lengths in transversal and axial directions respectively. In both graphics, that is an initial plateau associated to the sustained spherical shape at the beginning of the videos. These initial values differ due to the curvature of the capillary that causes some distortions in the microscopic images. As the capsule enters the constriction, Li starts dropping and Lx starts growing until they reach their minimum and maximum values respectively, indicating the capsule's maximum deformation. Then, as the capsule flows in the divergence zone, the parameters start going back to their initial values until the spherical shape is resumed, characterizing the reversible deformation. When the constriction causes the shell rupture, the position versus time behavior is similar to what we saw for the reversible deformation case. The capsule that has a diameter of 175 in this case gets trapped in the entrance of the constriction and slows down. However, this capsule is not able to pass intact to the constriction and the measurements stop when the shell ruptures, as you see on these images. The microcapsule takes the slug shape as it enters in the convergence zone. Because the rise in pressure is not enough to make the microcapsule pass to the divergence zone, it gets stuck in the constriction. Then the shell is stretched until it ends up rupturing. So the inner content is released to the medium and the pressure reaches back the initial plateau. Even though we were able to measure the pressure response in this case, the reduction mobility would be higher if rupture did not occur. The rupture is also indicated by Li and Lx as they drop and grow respectively and never reach back their initial values. Again, these initial values related to the spherical shape differ due to the capillary curvature that distort microscopic images. In this case, the severe deformation imposed by the reduction in the capillary diameter stretches the shell material until it gets too thin and ruptures. So here is the table with the capsules used in the experiments again, now including the pressure drop and the type of deformation observed in each case. At least 5 measurements were made for each batch of capsules. Here you see the average for each case. For the last 2 batches, 4 and 5, the ones with the smallest capsules, it was not possible to measure the pressure drop because it was below the instrument's resolution. Only capsules of batches 3 and 5 flowed intact through the constriction. Now let's look closely to this data to understand why. Analyzing the results, we see that pressure rises with the diameter when the shell thickness is fixed. This makes sense since it is more difficult for the biggest capsules to flow through the constriction than it is for the smallest ones that do not need to deform that much to pass. We can see it by comparing here batches 1 and 3 and batches 2 and 4. A similar behavior happens when the diameter is kept fixed and the shell thickness is increased. Pressure drop also increases. The batches 2 and 3, for example, they indicate that it is harder to deform a capsule that has a thick shell than a capsule with a thin shell. Moreover, in this case, the thick shell seems to withstand the imposed deformation without rupturing. So diameter and shell thickness do affect the pressure response, but alone may not be enough to establish what type of deformation the microcapsule undergoes. Nonetheless, looking to these ratios here, it seems that the diameter and shell thickness can have a strong effect on how a microcapsule responds to the external stress imposed by the constriction, especially if properly combined. So here we have a map that summarizes all data on the, based on the ratio between shell thickness and microcapsule diameter. For specific constriction diameter, the map shows that the correlation between capsule diameter and shell thickness defines if shell ruptures or not. It indicates that for a certain microcapsule to constriction diameter ratio, there is a minimum ratio between shell thickness and capsule diameter that guarantees reversible deformation and therefore microcapsule integrity after passing through the constriction. Thus, there are 2 zones determined by the mechanical properties of microcapsules: a rupture zone and a reversible deformation zone. The capsules in blue with low shell thickness to capsule diameter ratio rupture being suitable for target delivery triggered by the external stress imposed by the constriction, while the capsules in red here with high shell thickness to capsule diameter ratio can be used for flow mobility control. Summing up, we are able to produce microcapsules with mechanical properties that can be tuned mostly by the flow rates of the phases that form them. We also related the shape that microcapsules assume during the flow through a constriction to the pressure drop associated to each phase of this flow. Then we established the conditions that lead to shell rupture associated with the shell thickness to diameter ratio, which seems to be a major parameter to predict inner content release. Our results show how microcapsules can be designed and produced to achieve the desired suspension flow behavior in confined spaces depending on their application. I would like to thank all the funding agents, my research group at PUC, and you for the attention. To learn about other applications of jello microcapsules and to see other lines of research, please check the lab's social media or send me an email.